Hello everyone. Today we will be looking at binary search trees. It is a data structure in the form of a binary tree that allows us to perform various operations. We shall see that the operations have a running time proportional to the height of the tree. This lecture corresponds to chapter 12 of your textbook. Before we begin, let's quickly look back at what we studied in the previous lecture. The topic of discussion was hashing. We began with an introduction to direct address tables, or DAT, and saw that it is a very inefficient solution to store keys when the universal set is very large, especially in memory-limited applications. We then introduced hash tables that use the hash function to store keys in the table. While hash tables use up lesser memory space, they usually result in collisions. To resolve this, chaining was introduced. The two possible implementations of chaining were using either singly or doubly linked lists. Then we saw how to devise efficient hash tables. We saw three methods: hashing by division, by multiplication, and universal hashing. Finally, open addressing was introduced, where the keys were stored in the table slots itself rather than in linked lists. To avoid collision, linear, quadratic, and double probing was studied with examples. So, we want to use a binary tree to support a bunch of operations that are useful in dynamic data structures. These operations are search, minimum, maximum, predecessor, successor, insert, and delete. Let's begin with the definition of a binary search tree, or BST for short. So what's a BST? It is basically a binary tree data structure where each node contains a key, a pointer to its left child, a pointer to its right child, and a pointer to its parent. If any of the children or parent is missing, the pointer is set to nil. If you think about it, the only node whose parent is nil is the root of the BST. It should be noted that the running time of these operations is proportional to the height of the BST. If the BST is a complete tree with n nodes, then the running time is O of log n. Whereas if the BST is a linear tree with n nodes, its running time is of the order of n. Let's look at these two BSTs. For example, in A, if we select the node 6, we see that all keys in the left subtree of node 6 have values less than or equal to 6. Similarly, all keys in the right subtree have values that are at least 6. Another interesting fact is that there can be more than one BST representation for a given set of keys. That is to say, the BSTs in A and B represent the same set of keys and only differ in the choice of the root. We have a balanced tree in A, which has a height of 2. On the other hand, we have an unbalanced BST of height 4 in B. So, irrespective of the structure, all BSTs have to satisfy the binary search tree property. This is something similar to what we saw in max heaps, which also are built using binary trees. Therefore, the binary search tree property is formally stated as given here. For any node x in the BST, if node y is in the left subtree of x, then the key of y should have a value at most as the key of x. If the node y is in the right subtree of x, then its key cannot have a value lesser than that of node x. With such a property in place, we can easily print out all the keys in the BST in a sorted order, or as it is commonly called, perform the in-order tree walk. The algorithm that does this is the in-order tree walk procedure, which takes the root of the BST as its input. The algorithm basically starts with the root, prints its left child, then the root, and then the right child in a recursive manner. Let's take a look at the pseudocode of this algorithm. This is the pseudocode of the in-order tree walk. As long as the BST has a node X, we recursively invoke the function on its left child, print the key of X, and then recursively call the function on the right child of node X. So both the BST examples that we saw earlier will yield 2, 5, 5, 6, 7, 8 as the in-order walk. As an exercise, try to think of how to implement the pre-order and post-order tree walks. Since we traverse each node in the BST of n nodes using 2 recursive calls on line 2 and 4, the in-order tree walk procedure takes theta n amount of time to execute. Now let's look at the operations that deal with searching for a particular key or a node with specific features. This is called querying and involves operations such as search, minimum, maximum, successor, and predecessor. These operations run proportional to the height of the BST, which in the average case is O of log n, and worst case is O of n. Let's begin with searching for a particular key, say k, in a given BST. So, if we are given the pointer to the root of the BST and the search key k, the search procedure should return the pointer to a node having the key k if such a node exists. If none of the nodes in the BST carries the key k, it should return nil. The pseudocode is given here. Line 1 checks if the tree rooted at x is empty or not, or whether the key of x is equal to k. In either case, the procedure returns x. On line 3, if k has a value lesser than that of the node x, then it recursively calls the procedure on the left child of x. Otherwise, it does the same on the right child of x. In the example here, if we want to search for key 13, we start from the root node 15. Since 13 is less than 15, we traverse the left subtree of 15, thus discarding the right subtree, as we know that the BST maintains the binary search tree property. Again, we compare 6 and 13. Since 6 is less than 13, we search the right subtree rooted at 6. Then we compare 7 and 13. Since 7 is less than 13, we search the right subtree of 7 and find the key 13 in the right child of node with the key value 7. So we traverse the path 15, 6, 7, 13. Note that unlike the in-order tree walk procedure, the tree search procedure only traverses one of the subtrees and not both. That is why it has a logarithmic running time. The tree search procedure we just saw was written recursively. For large trees, however, recursive approaches are lesser efficient in terms of memory management, as it causes stacks of activation records to keep track of the recursive calls. So the code can be further improved by replacing the recursive structure with a simple while loop as shown here. If the tree has a large number of nodes to search among, use the non-recursive search procedure instead. What if we want to find the node with the least valued key or the highest valued key? That's when we use the minimum or maximum procedures shown here. Thanks to the binary search tree property, it is very easy to see that the minimum key will always be in the leftmost path from the root. And the maximum key is in the rightmost path. So in this given example, the minimum key would be in the last node on the leftmost path, while the maximum key would be in the node on the rightmost path. Sometimes we are interested to know the successor or predecessor of a given node in a BST. The successor of a node X is the node with the smallest key greater than that of X. The structure of the BST allows us to easily determine the successor of a node without comparing the key values. The procedure that does this for us is shown here. The tree successor procedure can be broken down into two cases. In the first case, if the right subtree of node X is non-empty, then the successor of X is the leftmost node in X's right subtree. This is found by the tree minimum procedure given in line 2. As of case 2, if the right subtree of node X is empty and X has a successor, say node Y, then Y is the lowest ancestor of X, whose left child is also an ancestor of X. The running time of the tree successor procedure on a tree of height h is therefore O of h. As an example, let us try to find the successor of the node with key 15. We first check case 1, that is, see if the right subtree of the node is non-empty. In this case, it is non-empty. So the successor would be the leftmost node in this subtree, which is the node with 17. And this node is returned using the minimum procedure. As an example of case 2, let us now find the successor of the node with key value 13. Since the node has no right subtree, its successor will be the root with value 15. This is because it is the ancestor of this node and has a left child, which is this node, that is also an ancestor of the node with value 13. Just to clarify, ancestor of node X is any node that is the parent of X's parent node. So according to case 2, the successor of the node with key 13 would be the node carrying the value 15. As an exercise, try to write the pseudocode for the tree predecessor procedure. We now reach the final set of operations, namely insert and delete. The thing that we should keep in mind about these two operations is that they cause the structure of the BST to change while maintaining the BST property. Inserting a new node into a BST is easy, but deletion requires a bit more caution as it is quite tricky. Let's begin with the insert operation first. Suppose you want to insert a new key, say V, into a BST. The tree insert procedure takes the pointer to the root node of the tree T and the node Z, whose value is set to V. Its left child and right child are set to nil. Starting from the root node, it traces a path downward looking for a nil value to replace with the new node Z. The pseudocode for this procedure is shown over here. In this example given over here, suppose we want to insert a new node with value 13. Starting from the root, we compare the key of the root with 13. Since 13 is greater than 12, we move in the right subtree of the root. Then we compare 13 with 18. Since 13 is less than 18, we move to the left. Then compare 13 with 15. Since 13 is less than 15 and 15 has no left child, we replace this nil with the key 13. Therefore, the lightly shaded circles show us the path that we traverse to insert the new key. And the dashed line over here shows the new insertion. Looking at the code, we see that the running time depends on the while loop. And the while loop runs as long as the tree is not empty. That means it traverses the complete height of the tree, which is log of n in the average case. The final operation is deletion. Suppose you want to delete some node z from a BST T, then there are three cases that can occur. Two of these three cases are easy, while the third one is a bit tricky. The first case is when the node z has no children at all. This is easy. We simply remove it and we modify its parent to replace the node z with nil as its child. Case 2 is when the node z has just one child. What we do in this case is we elevate that child to take z's position in the tree and modify z's parent to replace z by z's child. Now, the third and most tricky case is when z has two children. In this case, we first find the successor of z. Let's call it y. We then move y to take z's position in the tree. The rest of z's original right subtree becomes y's new right subtree, and z's left subtree becomes y's new left subtree. This case is tricky because it really matters whether y is z's right child or not. Let's look at this in more details. The inputs to the tree delete procedure are the pointers to the root of the tree T and the node that we want to delete, that is node Z. So if Z has no left child, then we should replace Z by its right child, depending on whether it exists or not. Assume that Z has no right child. That means its right child is nil. In this case, we deal with the situation in which Z has no children and we can just remove it without making any changes. But if Z has a right child, then in this case, what we do is we replace Z with its right child, as shown in this figure over here. Similarly, if Z has only one child, which is a left child, what we do is we replace Z by its left child, as shown in this figure. So these correspond to the first two cases that we discussed earlier. That means Z has no children or has one child. The case that remains to be investigated is when Z has both left and right children. In that case, we have to find the successor of Z, that is Y, and this successor would lie in Z's right subtree and should have no left child. What we then want to do is remove Y from its location and replace it with Z in the tree. If Y is Z's immediate right child, as shown in this figure, what we do is we replace Z by Y, leaving Y's right child alone. So what we can do is just bring Y, put it in place of Z, and move everything up. So this is what we would get. If Y is not the immediate right child of Z, then it should be the node in the leftmost part of the right subtree of Z and should have no left child, as shown over here. In this case, what we do is we first replace Y by its own child, which is X, and then we replace Z by Y. This procedure is shown over here. As we saw, case 3 requires moving subtrees around in the BST. The procedure transplant actually does that movement for us. So transplant procedure replaces the subtree rooted at some node U with another subtree rooted at node V. While doing so, the node U's parent becomes node V's parent, and U's parent ends up having V as its child. The pseudocode for tree delete procedure is as shown over here. As input, it takes the pointer to the root of the tree T and the pointer to the node that needs to be deleted, which is Z. Each line in this procedure, including the calls to the transplant procedure that we just saw, takes constant amount of time to run. except for line 5 where the running time is proportional to the height of the tree. Therefore, the tree delete procedure runs in OH time depending on the height of the tree, which is H.